have poured distilled water into these two beakers, standing spout to spout. Electrodes connected to a high voltage source have been lowered into the beakers. We set the voltage at 10 kV and start moving the beakers apart. It's incredible, but the water does not break apart, and we see a thin water bridge appearing between the spouts. It connects the parts of water in the two beakers. The bridge is drawing out, but its diameter hardly changes. At the moment, the length of the bridge is 12 mm, and its diameter is 1 mm. We can carry out this experiment in backward order. Let's move the beaker spouts apart to the distance of 1.5 cm, apply high voltage and start gradually moving the beakers towards each other. There are sparks flashing, electrified drops, and whole streams of water passing between the spouts. And then one of the streams closes the electric circuit, and so a stable water bridge is formed. When there's a several kilovolts potential difference between two vessels with water, free charges start moving in the water, and the induced opposite charges get attracted. They stretch water streams and form the bridge. What keeps the bridge suspended? Why doesn't it break? The point is that surface tension forces act upon the bridge's ends, and their resultant is directed vertically upwards. It is this force that compensates for the gravity force acting upon the bridge. But what's the role of electricity in this story? Will the already existing bridge hold if we switch off the high voltage? Let's carry out an experiment. We're going to decrease the voltage gradually and record the process using a speed camera. When the voltage drops to 6 kV, the bridge, affected by surface tension, breaks into several drops. We can conclude that the role of an electric field is to hinder the development of Plateau-Rayleigh instability, which makes the water bridge break into drops. Imagine a neck appear on the bridge. Electric current density would be greater in it, so, according to Ohm's law, electric field intensity would increase as well. Field-oriented polar molecules of water get drawn into the more intense field area. The water pressure in the neck increases, and the neck dissolves. We light the bridge up with a flashlight and see that there are water vapor spires rising above it. This means that the water in the bridge gets heated up nearly to the boiling point. The voltage of 10 kV has been applied to the bridge. The current of 0.2 mA is passing through it. This means that the heat power of 2 watts is released within the bridge. If there were no heat removal, the water in it would boil within several seconds. However, the released power is used to evaporate hot water. New portions of cold water keep arriving, so the bridge can stay suspended between the beakers for many minutes.